So thanks a lot for the introduction. Yeah, I'm glad to be here, which used to be my home, but my office was at second floor in Resnick, and I also used to deal with condensed matter once upon a time. And thanks for the invitation. So let's start. Okay. So this is where we are. It's okay. So this is I would like to start by thanking my students for the great work that I've been doing for the last few years, 10 years actually. And this is the most recent picture I have. And you probably see many familiar faces. We've been funded mostly by the Israeli Science Foundation. And we have been lucky to work with several companies in the field of quantum computers. And in particular, I would like to acknowledge Rigetti, that hosted me for a postdoctoral, for a sabbatical couple of years ago. So, and in particular, I mean, Matthew Rigor, who is now moved to the Google team, and Maxime Dupont. I will mention work done with them. And also collaborators from Tel Aviv University and India, and in particular Iran, who is a co-PI in this quantum ISF that really gave a boost to the project that I will present today. Okay. So computer platforms. There are many different ways to build a quantum computer. And there are two that are currently believed to be the most promising ones. One is superconducting circuits that is also being built here in the nanotechnology building in the lab of Michael Stern, and trapped ions. They have different properties. So superconducting circuits are easier to scale. People think of lithography, so it's in principle very easy to scale it up, as we have scaled up regular computers. So that's why people believe in superconducting circuits. The problem is that condensed matter systems are more dirty, so it's a little bit hard to make them with long coherence times. And in contrast, trapped ions are very well isolated. They live in a vacuum. You control each atom, and they have longer coherence times. So it's one can achieve better fidelities with trapped ions. The problem is scalability, because you have a trap, and now if you want to make more ions, you need to either squeeze them more, which requires stronger forces, and at some point it breaks down, or what you can alternatively do is building a larger trap, but there is a limit to it. So that's these are the limitations. Okay, so there are many other different ways to build a quantum computer. And in particular, recently in December, there was a paper by Cuera, that is the MIT Harvard Rydberg Atoms quantum computing effort. And what you see here is these Super Mario pictures is actually each of the dots is a single atom, is a single Rydberg atom. So they have the capabilities using these optical tweezers to capture atoms. And then what they can do, they can move these atoms around. And in fact, the gates are done by taking an atom close to another atom and then applying some Rydberg excitations to make them interact. And they have a very, very long coherence times. One point I would like to mention when speaking about trapped ions and Rydberg atoms is that what really matters is, of course, the ratio between the time, the gate time and the coherence time. So that's the ratio that tells you how good your gate is. But there is also another parameter that is important, which is the lifetime of a PhD. So what I'm trying to say is the fact that the base gate time of a Rydberg atom is in the kilohertz or tens of kilohertz means that you have a computer that runs on a 10 kilohertz clock. And this is really a very slow clock. So, of course, the ratio between the coherence time and the gate time matters, but it also matters the gate time itself, because it will tell you what is the prefactor that is in front of anything else you're doing. And that's something that usually people, sweep under the carpet. So how long did the computation take? Because if you need an exponential or a very large number of gates, and each gate takes a millisecond, then you may get into troubles. And other ways to build the quantum computers are the photons. Usually photons give rise to what is known as a measurement-based quantum computer. So it's a quantum computer that's built in a little bit different way than the usual gates that you're all familiar with. Nevertheless, it has been demonstrated to be equivalent. So having a measurement-based quantum computer, universal quantum computer, they have the same capabilities. And you know that there is a company here in Israel that is building a photonic quantum computer, which is a quantum source. And I'm mentioning this because my former student, our former student, David Dembelski, is now working there. So that's why I like this in particular. This is a condensed matter seminar, so you can also do a really condensed semiconductor, like these two DAG experiments in which you place gates, and then you can control the electrons. So you have electrons hopping around, and then you're happy. So I was told that it's very important to see if the audience is listening. So I would like to make a small poll to see if you're listening. And so we are going to do it like in class. You need to vote, and you can vote with your feet, but don't raise your hand so that nobody will know. So you put it on your chest. You use one finger, either of the one finger. One finger means that there are 5 ways to build the quantum computer. 10 ways, 20 ways, 30 ways, or 50. So please vote.
No, but what is the question exactly?
The question is how many ways are there to build how many platforms are there to build the quantum computer? That's the question.
Zero is not enough.
Okay. How many ways have been, experimentally demonstrated? How many different ways, people have demonstrated the basic items of a quantum computer? Doesn't mean that this is a quantum computer that will work, but how many ways are there?
Will there be a second question? How many quantum computers actually work?
No, there won't be such a question. Yeah, so the students are also invited to vote. You can also use your previous knowledge. So Lev is the only one who is brave enough to vote.
How did you vote?
Yeah, like that.
You vote. You need to place your fingers on the chest.
3, 4,
1. Okay, Hanan, thank you. Someone is alive in the audience. Okay. Yeah. Okay, good. So I see many of you are voting. That means
you mentioned 5, but there are more that you didn't mention.
That's exactly the point. So that's why people are mentioning 10, because there are more. So I mentioned 5 of them. The reality is that there are at least 28. This is very annoying. How do I get rid of this? More. Hide floating menu. Okay, it's done. Yeah. So, but this is also annoying. How do I get rid of this?
Okay.
Yes.
Yes, leave?
That's okay.
Yes.
No, that's it.
No, what do you mean?
No, you don't want the bar.
Yeah, this bar is hiding my size.
So
Okay. Okay.
Again,
Hold on.
yes.
Okay, nice.
Don't touch anything.
No, don't touch it. No, just because this is a slide that I took from Serge Bell, so it was important to acknowledge that this is not my own research. But so there are many different ways that people have discussed how to build a quantum computer.
I like line 28.
28 and more, yes. Okay, so yeah, then of course this doesn't work. Okay, good. So then the question is, okay, quantum computers, what are they good for? So I don't want to answer this question by myself because, I'm a little bit biased. So that's why I'm bringing, Microsoft, which I think is a big company and has invested a lot in different types of quantum computers to give the answer for that. So I'm now going to show you a movie from the Microsoft quantum how is it called?
Propaganda.
There is a limit to how much.
So here is the movie.
Be nicer.
Running a quantum program on a real quantum computer using Azure Quantum is magic. It's amazing.
Azure Quantum
Quantum enabled us to create a first-of-its-kind course in which students analyze how real quantum computers perform. It was a unique opportunity to combine learning with doing in quantum information. After completing a series of team-based projects, students were able to design their own research problems and run experiments on the IonQ machine, accessed through Azure Quantum. These students had previously studied quantum computing in theory, but this was their first chance to program and evaluate real quantum devices. It was an incredible experience for them.
We used Quantinuum hardware accessed through Azure Quantum for testing the quantumness of the computer and comparing it with classical computers. We've challenged the computers to solve a certain puzzle. The classical computer had a success rate of 87%, but by taking advantage of non-local effects, the success rate of the quantum computer was a striking 97%. This game essentially proves that the quantum computer is quantum. The Azure Quantum Credits program has given us the opportunity to be the pioneers of this type of research.
Our project was an academic research collaboration between the Technical University of Denmark and KPMG. It involved neural networks, which are computer systems that mimic the human brain. By accessing hardware through Azure Quantum, we use quantum computing to train and control neural networks. People and organizations, they are beginning to realize the extreme power that lies in quantum computing. This is something that we can truly harness.
The word is out. Quantum computing is going to change how we solve problems.
Okay, thank you. So in this very unbiased movie, you have heard about what computers are good for. And I think what the community believes are three main aspects of it that has been mentioned in the movie. One is about education. So how to learn quantum mechanics in a funner way. And so, you know, we are an academic institution. Education is part of our goal. Optimization, so related to industrial problems. Applications of solving combinatorial optimization problems. And the third direction is the one of quantum simulations. Here today, so this is in general what's going on in Israel. So in terms of education, actually, Mafat has been promoting a quantum IL program that will start. It has already started, and there are excellent teachers, including myself, of course. And Eliyahu Cohen from the engineering department. In terms of optimization, Quantimize is the solution. So this is a startup that I'm a chief scientist, and we are working really hard to make this work. It's hard. It's really hard. And if you're interested, you know, I can give you more details, but no. Now, and what I would tell you today is about quantum simulations. Okay, so that's basically the introduction. So what does it mean to make a quantum simulation? Think of your favorite material. So again, condensed matter, graphene. You are trying to solve the ground state of this material, and the way you could think of doing that is to find, you know, the description of the ground state, and the ground state is basically a vector in the Hilbert space, but the Hilbert space is really large, which means that your vector is very, very large. Not to speak about the Newtonian itself, which is even larger, right? It's in the square, but even just storing the state itself requires a very large computer. You know, it's, as you know, 10 to the 10 is 1,000, so 10 to the 20 is 1,000,000, 10 to the 30 is et cetera, et cetera. So very rapidly, when you have, say, 50, 60 qubits, you just cannot store that state. So what we like to do as theorists is to use an effective description to do an approximation. In particular, quantum field theories have been a very powerful tool to describe these interacting problems. Of course, you can also do that numerically. Again, it's a different type of approximation. We are all familiar with the MRG and related methods, so using classical supercomputers. Or there is the field of quantum simulation, which was actually pioneered by Richard Feynman with this famous quote that it says, if I try my best to make the equations look as near as possible to what would be imitable, okay, imitable, that's by classical probabilistic computer, I get into trouble. And the problem he's describing essentially is a very known sign problem, which tells you that because in quantum computers these amplitudes are complex, you cannot just sample it very easily. Okay, that's known as the sign problem. And so what he said is that then the solution is just use another quantum system. If you want to solve a quantum problem, don't use a classical computer, use a quantum system. And this has been pushed forward tremendously in the field of ultra-cold atoms, starting from the last century with the realization of the Bose-Einstein condensate in ultra-cold atoms. They understood that they really have something very powerful in hand, and they developed this field of quantum simulations. I think this was really the first field in which this idea really got very, very, got very nice results, although there are some limitations. First of all, in terms of the temperature, they were not able to solve the Hubbard model, so they are useless. And so that's why we come and say, no, don't use ultra-cold atoms, use a quantum computer. It's also a quantum system. It's a many-body quantum system. You can use it to do your favorite quantum simulations. Of course, I'm not, the truth is you should do everything together, and you can really think of the ultra-cold atoms as a simulator of your quantum computer. The quantum computer simulates the ultra-cold atoms, and then the material is another quantum simulator. I think what is really interesting is to connect together all these fields. Okay, very nice. So I think I've motivated why quantum simulations are interesting, and now what can you do? So I'm now going to show you 3 examples from the literature, without studying that in detail, but just examples of Nature papers from the couple of years where people apply these ideas of using a quantum computer for quantum simulation. So one work is actually a very relatively recent one by IBM, where they speak about the utility of a quantum computer. And if you, in practice, what they did is to simulate the dynamics of the transverse Ising model. Okay, so that's the claim of utility. People claim it's not useful. Who cares about the Ising model? They also claim that you can simulate the Ising model elsewhere. So, there are all sorts of discussion around this very interesting article. But okay, this is an example of a quantum simulation. You can study the dynamics of an interesting many-body problem. So that was the achievement. Another Nature paper, also actually this is from 2022, from Zhejiang University, where they created a Fouquet topological phase. So I'm sure you have all heard lectures about topological phases, but this is a Fouquet topological phase, and they were able to simulate it on a quantum computer. But I think, Google, Ganavet Atzaga, right, they were the best in terms of PR, and they created a wormhole in a quantum computer, and people got scared about this wormhole, that it will absorb everything we know, and we will disappear. They did a PR, an amazing work of PR. So these are examples. Okay, there are many examples. Of course, what I came here today to tell you about is our own work. We've been very active in the last 3 or 4 years doing quantum simulations, and I chose for you 2 examples, 2 projects, which I think are more related to the audience here. One about topological phase transitions, and another one about Bose-Einstein condensates. So these are the 2 projects I would like to present today. Okay. So questions about the introduction? Very clear. Nice. Are you convinced? You should all abandon what you're doing and doing quantum simulation with a quantum computer? Yes? Okay. 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 Anyway, so let's start. About topological phases of matter. So as you all know, from statistical mechanics, I understand there was an exam in statistical mechanics yesterday, right? So you all know that there are phases that are either ordered or disordered, and if you think in terms of, instead of spins, you call it qubit. So if you take a qubit, so if you call it 0, 1, you are now a quantum information theorist instead of a physicist. So I'm doing quantum information. You see, these are not spin up, spin down, 0 and 1. So there is an ordered phase, phase 0, 1, an antiferromagnet, and a disordered phase, which is disordered. But as it's, Landau thought this is everything you could ever possibly see in your lifetime. But then people understood, starting from some examples, people understood that actually there are more phases. There are more phases. Oh, yeah. something quite stupid. Okay. So there are more phases, and in particular, there are phases that are called topological phases. And this is the work for which Duncan Haldane was awarded a Nobel Prize. And I'm also been interested in this topic since my master's, and I learned from that you should always have in your slides. Remember, this is for the students. You should always have in your slides somewhere where there is your name and the Nobel Prize medal in the same slide. It's very, very important. So that now I have that. I accomplished the task. Okay, good. Nice. So what are these topological phases? At that time, we didn't quite even know that this was a topological phase, because this was just really the beginning of. At the beginning, there was just one example, which was this Haldane phase, for which Haldane got the Nobel Prize, and we understood. I mean, my advisor had told me what to do, and Erez, what they understood is that you can also have the same phase in other models. So that, and then, you know, as time went on, people understood that, oh, also in that model you have a topological, and there's people then realized that there is a whole classification of topological phases, and in particular, these are known as symmetry. Yeah, as
quantum music.
Playing music? That's someone is listening to us, guys. So these are known as symmetry protected topological phases. So they're specific type of phases. And let me give you a very, so before we go into details, so how can you realize such a phase? So I'm going to give you a very simple, how can I create an ordered phase? So for me, the ordered phase in this work is going to be just a 0, 0, 0 state. So to prepare a 0, 0, 0 state, you do nothing. By the way, do you know how in a quantum computer they prepare the 0, 0 state?
They do not.
They do nothing. You wait. Yes, you wait, and it's inside the dilution free, and then all the qubits go to 0, and you're happy. So that's the way. This is a circuit. Okay. How you create a disordered phase? For me, a disordered phase would be a state in which you apply this H to which the qubit. So you know that the H it's Hadamard gate, and what it does for you is a superposition of 0 and 1. So here now, this is the most disordered phase you can ever imagine, right? You have all the options and with the same probability. So it's really, so for me, this would be the ground state of some Hamiltonian,
But
which is, yeah.
But to be honest, that's not a disordered state, right? It's an ordered state, just in the x direction.
Yeah, so it's like a paramagnet. Okay, so this would be, you know, the ferromagnet, and this would be the paramagnet. So if you have in your mind an Hamiltonian, then this would be the ground state of the ferromagnetic side of the Hamiltonian, and this would be the ground state of the paramagnetic side of the Hamiltonian. However, you are right that they are both in some sense ordered, and this is indeed the case, that they are both local. What you really want to say is that they are local, you know, these are both local phases, so they are very simple to understand. And then, you know, you can map one to another, and it's not really, I call one order, one disorder, but whom you call order and disorder is just a matter of which direction you're looking at, essentially. So they are both non-topological phases. And instead, this would be an example of a phase that is actually topologically ordered. So let me just show you before, how does it look like in terms of the spin? So you see that it's also disordered. The zeros and ones appear randomly, but there is some hidden order. That was the title of my paper. It's also known as the string order, which tells you that when you look at the ones, they appear randomly, but actually they appear in pairs. Okay, so the one after some one will become another one. And you will not have, you can have as many zeros as you wish in between, but the ones, when they appear, they have another one that is next to it. It's like some sort of pairing of these ones. Okay, so that's what is the nature of these topological phase, and how you can create it. So I don't have enough time to explain how this works exactly, but it turns out that if you prepare these state, now you see, so here I'm applying the Hadamard as before, and then I have these control Z gates. So you see that it's now a state that is entangled. Okay, it's an entangled state. You cannot disentangle it easy. It's not unlike this one that is local. This one is non-local, and indeed the order of this state would be disordered. It's related to this topic of cluster states. So if you heard the word cluster state, this is the simplest example of a cluster state.
So disordered state for you is a product state, and the topological state is an entangled state. So why don't you call it product states versus entangled state?
Okay, very good. So what I'm showing you here is extreme examples of a very local one and a very topological one. You could ask what's in between. So here, this is one example, and this is another example. Now, the statement is that you can have entangled states that are still disordered. Okay, when you measure the order parameter of the non-local order parameter, you will see that the non-local order parameter is 0, and you can have many, many other states that have some entanglement that are ordered. So being, topological, non-topological goes beyond the entanglement. You are perfectly right that it's a necessary condition. So if there is no entanglement, certainly there is no local order. But having an entanglement itself is not sufficient. You need to have a specific type of entanglement, and indeed this is what I'm going now to explain. Which type of entanglement, what is so special about the entanglement of those states? That's exactly the question that I'm going to answer in my next slide. But beforehand, what I would like to tell you is that you can realize those phases. So you can realize the topological phase as the ground state of some Hamiltonian. Which Hamiltonian? This one. So this is known. You recognize this, the Ising Hamiltonian, right? These ZZ terms and the X term. However, this is called the kicked Ising model. So it's a model in which you first apply Z, then apply X. First, then a Z, then X, okay? Unlike the usual case, you have an Hamiltonian that contains both Z and X, so you are applying both at the same time. Here, what I'm doing, I'm first applying one and then the other, okay? I alternate, so it's like a kicked, it's called the kicked Ising model, okay? So there is one additional time scale, which is the time scale of these kicks, and it turns out that this model has actually 4 phases. So the random Ising model itself, you have only Z, Z, and X. It has 2 phases, right? Ferromagnet, paramagnet. But when you add also these kick, it gives rise to 4 phases. The reason for the experts, where are the experts? The reason for the experts is that when you fermionize this, when you move to the fermionic Jordan-Wigner transformed description, the different phases correspond to different number of Majorana fermions. So as you all know, the ferromagnet and paramagnet correspond to having one Majoran, not having one Majoran. But when you have a periodically driven system, these Majorans can appear both at 0 energy and at pi energy, and then you can have 4 options: no Majorana, 1 Majorana 0, 1 Majorana pi, and 1 Majorana 0 pi. So this the 0 pi is a Majorana, is a topological phase, while this pi phase is just a time crystal. Okay, so I mentioned that Google. Did I mention it?
I mean a parametric resonator.
So we believed, we believed that Google has also a paper about time crystals. We didn't realize time crystals because we thought they were not interesting enough. We actually focused on this topological phase, and so yes, this is the paper this is the Google AI Nature paper on time crystals.
So Emmanuel, the idea is that a single Majorana mode becomes gapless at pi at the 0 pi. That's
so I want to complain with the organizers because this, I don't know why, but this is not. Yeah. Okay. No, I mean I really need on my slide. Yeah, I can. Okay.
No, but you see all the slide.
Sorry.
It just is.
You can see it. Yeah. No, it's fine. This is so this is a work. This is the Google work about the time crystals. The question, sorry?
Yeah. So you mentioned these Majoranas.
Yes.
So the idea is that the 0 pi phase is where you have a gapless Majorana mode at pi.
Both 0 and pi.
Both 0 and pi.
Because you see, having one Majorana at 0 is the ferromagnet. having one minor at pi, it's a ferromagnet also, but that alternating. Exactly. So this is what you see here. This is the magnetization as a function of time, and it's like in a ferromagnet it should stay constant. Here it almost stays constant, except that it flips time every time. Okay, so that's a time crystal, something that oscillates between up and down, up and down. Then there is a question about disorder, interactions, blah, blah. It's a very nice paper. I mean, I think it's a very nice experimental paper. The idea is that this is stable, so it's not just, you know, I don't want to enter into the time crystal discussion. Good. Okay, excellent. So what did we do? What we did was actually to think about an adiabatic transition from the topological phase, from the zero phase, to the ferromagnetic phase. That was the idea. So how you do that? So we have a parameter theta. So what we do, we alternate ZZX, 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 but instead of alternating constantly. So the same ZZ, the same X, the same ZZ, the same X. While I'm doing this, I'm also moving, okay? I'm also adiabatically moving, and I'm going from the topological phase to the ferromagnetic phase. And so how can I detect the presence of such a phase? So the way to, as we all know, something that is peculiar to these symmetry-protected topological phases is the presence of edge states. That's one, you know, typical feature of the, okay, it has showed us that it's not necessary. I mean, sometimes you also have SPT without edge states. I know that, but in general, you know, for us, simple people, when you have an SPT, usually you have an edge state, and this is indeed what you see here. So I'm now going to show you a simulation of 50 qubits, and you may ask, how do you do it at 50 qubits? There are two. So first of all, this is because this specific model, it's an integrable model, you can map it to free fermions, and also because I have a very good student who was able to implement it, which is Daniel, who was able to actually do the calculation, and also Angelo helped us with that. And by the way, we actually discovered this adiabatic, because you may ask, what does it mean to do an adiabatic Floquet thing, right? You are doing, so it's not really adiabatic, you are doing this and that, so it's not trivial. I mean, there was, and actually, yeah, I think our paper was the first one on this topic. Who cares? Anyway, what you see here is that you see this. What you should look at is this, you know, red, blue, red, blue, red, blue here, which is an edge state. So this is the topological edge state. So it's an edge state topological, but it's also, you see, oscillating with time, right? That's what's special about the Floquet topological, because it's not just topological, it's Floquet topological. What is the difference? In a topological, you have an edge state, but in a Floquet topological, you have an edge state that oscillates between 0, 1, 0, and 1, 0, and 1.
This is the expectation value of each.
These are each qubit. This is a theory paper. This is the theory side of it. So you have 50 qubits, and this is time. And what you see is that the edge states disappear, right? Right here, there is no edge state anymore. And the reason is that I'm going from, this theta parameter goes from 0 to 250. I'm moving from deep inside the Floquet topological to the ferromagnetic phase. So I'm killing the edge state. That's what you see. There is an oscillating edge state that at some point dies out.
What is the quantity that you're plotting?
The spin, just the spin.
The expectation value of this.
Yeah.
The local spin.
Yeah.
So why is the bulk 1 in the 0 to 0 in the?
It's well, it's so. It goes to 0 because, as you know, the ground state of the ferromagnetic state is 0, 0, 0 plus 1, 1, 1, 1, 1, right? So 0 here means, so that's the answer. And why is 0 here? That's actually a choice. You could have chosen it otherwise, but you know, it depends on which initial. So there are two initial states that you can start with depending on this edge state. So I don't have a good question, a good answer. But what I can tell you is that what you should see here is that these edge states are spreading. So initially they're very localized in the edge, but then when you approach the phase transition, they becomes more and more, delocalized. That's what you should see here.
This is done on a quantum computer?
No, this is done on a quantum computer for 4 qubits, and you can see that it's an ion Q quantum computer, and you can see that yes, there are some edge states, you know, that disappear at some point. It's cute. This is actually. Yeah. So, but let's try to understand it.
Just to understand, when you measure you propagate, you measure, then you cut at the beginning.
And then I repeat them many times, and I pay for every shot. But let me try to understand. So I said these are symmetry resolved symmetry topology. These are symmetry protected topological phases. So how can we understand them? So for that, let's discuss a little bit what does symmetry do. So symmetry means, that's all you all know, everyone knows, that if there is a symmetry, it means that you can diagonalize together the symmetry operator and the Hamiltonian. So your ground state is also an eigenstate of the symmetry operator, right? Everyone agrees with that? Okay.
I mean, there are like 3 prong states in this one.
Okay.
Okay, so you want us to monitor it?
So I'm saying if there is a symmetry, what does it mean? It is symmetry, it's an operator that commutes to the Hamiltonian. So if 2 operator commutes, it means that you can diagonalize them together. So that means that you can always find, if there is a symmetry, you can always find a common eigenstate of both. So that for me means that that you can find a ground state that is also symmetric with respect to the symmetry operator. Am I missing something?
Well, I guess depends what you have in mind. If you're thinking in terms of many body Hamiltonian, or thinking in terms of single parts.
No, many body. So everything is many body.
That's all right.
Okay, thanks, Steve. That's an important. This is indeed. I mean, what makes this problem interesting is indeed, in generic interacting systems. So that's fine. Now, something I didn't know, I learned from Iran, is what happens if you look at the reduced density metrics. Okay, so that's something there is one thing you always try to learn from one lecture. This is the one thing I try to bring I would like you to bring home, which is that what happens if I look at the reduced density metrics. Now, when I look at reduced density metrics, that conservation is not true anymore. Let me give an example. Let's assume that the conservation is conservation of the total number of particles. It means that I can always find a ground state with, say, 10 particles. Okay, I have 10 particles, then I can find the ground state for that 10 particles. Now, when I take the reduced density matrix, you all know what the reduced density matrix is. No?
Everyone knows.
Everyone knows. Is there someone who doesn't know what it is? Okay. Reduced density matrix, it simply means that you look at a subsystem. You take the whole system and you integrate out, you trace out, you forget about the part of your system, and you keep something out of it. Okay, so that's called, and what you get is an operator. It's called the reduced density. It's just a description of a subsystem. That's it. So now in the subsystem,
like mean field theory, similar philosophy.
So in the mean field, it would be when you integrate out everything except one side. So yes, but here I want to, in general, here what I have in mind is you take your system and you cut it into 2 halves. So you're forgetting half of it, but still keeping a large bulk of it. Now, so you're in like an extreme limit where you just look at one side. Here I want to have to integrate out, a big chunk, but also keep another big chunk. That's what I want to have in mind. Yes. So what happens? Same thing on the top. So I have 10 particles in total. When I look at the subsystem, that 10 particles not conserved anymore. I could have 6 or 5 or 4. There are fluctuations. Okay, so that's related to your question of entanglement. These number fluctuations are strongly related to the entanglement of the 2 parts, right? If there was no entanglement, then this story wouldn't work. Then, okay, so that's it. So what happens, nevertheless, is that the reduced density matrix is block diagonal in the density operator. Okay, that's one can show that, but you really need to just sit down for a moment and write it, and then you can convince yourself. For the moment, you just believe me. And that's the one thing you will take home, that you need to believe me always, and that is that the reduced density matrix commutes with the symmetry operator. So what does that mean? That means that when I look at the reduced density matrix, I can diagonalize it together with the symmetry. And this gives me a way to distinguish trivial phases from symmetry protected SPT phases. So it is always the case, by definition, that the reduced density matrix will be block diagonal. Okay, block diagonal just means that if I have in total 10 particles, I could have 6 or 4 or 3. I cannot have, I cannot have off diagonal terms that sort of create a particle in the middle. Okay, that's the idea. So in this case, it means this is an operator that has only 2 terms, right? Spin up, say, like a spin. So then I can look at the symmetry resolved. So these are the 2 symmetry resolved and reduced density matrices. Yes? No? Yes? Okay. Also
So the idea is that this kind of equal size blocks can be accidental, but in the topological phase, it's going to be robust.
Yeah, exactly. I'm saying two statements. First of all, that is always block diagonal. Whatever you do, if you have a symmetry, the Gaussian symmetry is block diagonal. Now you can ask, are these two parts equal or not? And if they are equal, either there is some, very strange thing happening on, or it's a symmetry SPT. I'm guessing if it is equal, you can always expand it to some SPT. So in general, the property is if you have an SPT, then these two are equal. Okay, that's the correct statement. So that's what you can do. You can look at these two. So this was a very nice work by Eran and Moshe. And then what we sort of extended was to idea. Eran extended it. I was programming the quantum computer. So he understood that what does that mean now if Floquet SPT? So the Floquet SPT means that the two are not equal. The up and down, the two sub-blocks are not equal, but they flip sign. Every time they flip. Okay, so you have so they flip exactly after one application, after one time period. They are equal on average, if you want. Okay, because it's it's red green, then green red. You apply it again, they flip again, so it comes back. If you want, it comes back every two periods. In general, this is not the case, and in general, if you apply some unitary, you will get another block. Okay, it's always block diagonal, but it could be something different. In an SPT phases, what you have is that it comes back over and over again. And this is what is shown now here.
But in principle, you can have many blocks like this.
So yes, so that's okay. This you need to read the paper of Daniel and Stella that I did not understand, in which they have more options, and then they discuss all the possible ways that you could have all sorts of SPT, Floquet SPT, in which they sort of what will happen, when you have more than two. Only two, you can either stay constant all over, or flip. These are basically the two options, but you're right, there could be. So what we are doing here is we are computing basically, this would be the trace, but you can also compute, right? So we are just looking at these two blocks, okay? So the idea is the following. We look at the two blocks. We look at the two blocks, yes. We look at the two blocks, and then separately, and we ask whether the blocks come back to their own or not. And this is what is shown here as a function of time. It's basically an extension of this idea of edge states. So edge states, you just look at the edge, but where does the topology come from? And the topology comes from when you do this exercise of taking the whole system, reducing it to the subblock, looking at all the moments of, this is the first moment, there are higher order moments, and what you should see here are basically two, there is, well, I mostly see these red, but I think in the original graph there were also blue lines yes, basically it oscillates. Okay, so you have red, blue, red, blue, red, blue. These are the two. This is what's happening. And what you see here is that this works very nice until some point, and then at some point everything breaks down, and that the breaking point is the transition. Remember that I'm doing an adiabatic move. I'm moving from the topological. You remember this? I'm moving from the topological to the normal, and in the topological, this order is always there. So it always up, down, up, down, up, down. You can stay there forever. While here, it starts oscillate. So you lose your time for okay, whatever. Okay.
This is like symmetry resolved entanglement. What is that?
This is symmetry. This is actually symmetry resolved. Yes, this is symmetry. This is symmetry resolved Rene entropies. This is an entropy number one. So it's just the trace. It's just the probability. And then if but the probability is just the polarization. It's just magnetization. So you're actually just showing me the integral over the previous graph, if you think. But in the paper you have also S2, which are the higher order Rene entropies. Okay. So yes. So that was in theory. And again, the quantum computer. We have 4 qubits. There is a theorem, but
now you can see the two lines.
You can see the lines, yes. What is nice is there is some correlation between simulation and experiment. And there is also a paper that appeared in Nature, basically doing the same thing that we did, probably with a little bit more of PR and access to a better quantum computer. That's actually a paper I mentioned at the beginning of my talk. It was submitted a month later than ours. It didn't cite us, but just you know that we did it before. Sorry?
4x4, how do you divide it into blocks 1 and 3?
You again, sorry, in the 2 blocks. So what you did, you need to do is essentially post-selection. So you need to measure that symmetry and then post-select the one that you like. And again, Daniel knows how to write a quantum circuit that will do that for you. I don't know exactly, but have some ideas. But Daniel did it. No, that's the idea. So you need to measure and then post-select. It's an interesting question. It's also related to the second part of the talk. We'll have 10 minutes for it. So yeah, so that was a very nice project. Questions? No questions? Okay, so now I would like to move to the second part, which is about simulating a Bose-Einstein condensate. So if, I mentioned wormhole, we cannot create wormhole, I apologize, but we can create a Bose-Einstein condensate. And don't be scared, it will not absorb you, in the same way that the wormhole by Google will not absorb anything. Okay, it doesn't really exist. The simulation, we are simulating something, that's the concept. Okay, good. So the question here is, first of all, what is a Bose-Einstein condensate? And I would like to give you 2 possible answers. Yes, originally this was a question for the audience, but there are experts, so I should be a bit careful. So I'm going to really show my answers so that I can give you the direction I want to go. And my 2 answers is, first of all, a Bose-Einstein condensate is the macroscopic occupation of some ground state. So the idea is that you have a trap. In the trap, you can think now of non-interacting particles to make our life simple. Then you say there is a trap, so think of just a Gaussian trap, right? So you know what are the eigenstates of it. It's just an harmonic oscillator. So you know to diagonalize it, and then you have bosons, and you can place the bosons wherever you wish. And in principle, the bosons will occupy, all the states according to the Boltzmann distribution, right? So there will be many states in the low energy state and many states above. And then what Bose understood by making a mistake in not being able to solve an integral, essentially, or thinking something is wrong was the integral. And then Einstein said, no, but your integral is fine. Actually, you discovered something new. Was that in some extreme cases, when you cool it really, really low, what will happen is that you will have many particles in the lowest possible ground state. Okay, that was the finding. So and this is called, and this is usually not the case. I mean, usually you have all sorts of states, so you have many states, but so many particles. So you don't just put all your money in one single investment, right? But if you cool down, then you can make that happen.
Stupid thing.
Yeah. So, okay, good. So the other answer is that it's more related to what happens if you take 2 Bose-Einstein condensates, and there is a matter of phase coherence. Okay, so the relation between the 2, I don't know, you need to take the course by Lev on Bose-Einstein condensates to understand, or my course, it's fine, I'll also explain it. But what is exactly the relation between these 2 concepts, we can discuss it, but what happens in a Bose-Einstein condensate is that if you want, it's not that complicated. It's the fact that because many particles are in a specific state, so they have a specific wave function. So there is, you can think of it like a macroscopic wave function that describes many particles. That wave function is a complex number that has a phase. And so that phase, you can think of it as the phase of your Bose-Einstein condensate. Okay, so that's the idea. So if you take 2 Bose-Einstein condensates, instead of having many particles with random phases and you get just a mess, what you should observe is that when you make them overlap, and you can just make them overlap by just letting them, explode, you just let them free, and then this overlap, and they create a very nice interference pattern. And in PowerPoint, it's really easy to see. Okay.
Why do you need 2? You have a global phase coherence in 1.
So if you have 1, then the question is how you make interfere.
All of the particles have the same phase.
Yeah, but the problem is that so what is the experiment you have in mind?
Just release them.
Release one. You have the same phase. Yes. You don't need to interfere too.
No, but what is the experiment? I mean, if you just let them expand, you will see a Gaussian that expands to a Gaussian, and you will see there. Yeah, but there is no concept of it. You're not measuring that phase.
I think phase is the same. Yes. So you need to divide it into 2. You have 2 different phases. That's what.
Yes, to measure the phase difference. Okay, so okay, yes, yeah. Okay, so then the question is, and that's actually a little bit more complicated question, which is what is the difference between a BC, a Nash condensate, and a laser? Okay, why? Because laser is done of photons and photons are also bosons. And then the problem is that, if you go to either direction, that doesn't really work. So if, let me put this on silent. Well, you can continue discussing. It's okay. Feel free. I'm also done. Okay, so if you believe in the story of the macroscopic occupation, a laser is certainly a macroscopic occupation. Okay, if you tell me it's about interference, well, we all know lasers do interfere. So in that sense, the BC and the laser are basically the same phenomenon. There are many answers to this question. I'll give you my own answer because it's the one we used in the paper. And the answer we gave is that there is one difference, which is that in the Bose-Einstein condensate, is the way I think of it in the experiment of a lab, what they use are atoms. So the bosons are atoms, and they do not just disappear. So there is a conserved quantity, which is the number of atoms you have in the trap, at least theoretically. While in the laser, in contrast, the laser is always, these photons are created all the time. So if I look in the cavity, there is always photons going out, right? Otherwise, you wouldn't know that it's a laser. And there is, some new photons that are generated. So there is, so in that sense, the number of photons is not conserved. And this is actually interesting in my opinion, because as you all know, number and phase are canonically conjugate. So like position and momentum. And then there is a question, because if I tell you that in the BC, the number of photons is conserved, so you have a good number, then the phase cannot be conserved because they are canonically conjugate. And you come and tell me, so what's going on here? Because you're telling me the phase is not conserved, but I show you an interference experiment. So how is it possible that the number is conserved, meaning that there is no global phase, and yet we see an interference experiment? The reason is that, yes, there is a phase, but that phase is undetermined. So what I'm doing here, I'm measuring the phase. So if you do and measure the phase, then the number, by the way, indeed, to measure it, you need to release the trap. Okay, so if you measure the phase, you can measure it if you want. It doesn't mean that it's defined to begin with. And indeed, if you repeat the experiment many times, what you will see is that you will see the same interference experiment, but at different positions. So that means that the phase is not defined. And that's fine because you want the number to be defined. Okay, good. Why in a laser, that's not the case? Because in laser, it's always the same interference. Like when I do an interference experiment, I would say the same interference. And that's fine because in the case of the laser, the number of photons is not conserved. So the global phase can be defined. Indeed, you can measure the electric field out of the cavity and it will give a number. So in that sense, these are the two differences. Okay, good. And when you immediately understand that you could also have a situation in which neither of them are conserved, nor the number, nor the phase. And that is, in my opinion, what people call a BC of light. And not everyone agrees, but that would be our opinion. So this sort of third option. And see, we are really running late. So what we wanted to do is to simulate a BC in a quantum computer. The way we do that, we prepare something that we call like a coherent state. So we prepare a state that has a well-defined phase. And in this case, it's very simple. Just prepare all the spin in the same position. So I hope you all see or you will learn this soon that you can think of this spin in the angle of the spin. So if you put it in a if you take your spin and put it in the XY plane on a Bloch sphere, then there is a phase, right? The phase between the 0 and 1 is indeed the position of the spin. So when I plug all the spins in the same X direction, it's like giving the same phase. So I'm like building a laser, if you want. It's trivial laser where the phase is always 0. Why 0? Because I give it 0. I put it 0. Then what I want to do is to prepare a BC. So what I want to do is a little bit like before. I want now to measure the number, okay, and then see what happens. So I want to measure the number without destroying the phase. Okay, and that's the way we do that. And then I can post-select if I want a specific number. So to visualize it, what I can do, I can define this order parameter. Okay, so that's the order parameter. It's like your psi. Okay, if you remember in superconductivity, there is a psi, right? This complex field. That's the order parameter. So in this case, you have a complex. It's a vector. Okay, so they have this real and imaginary phase, and I plot it. Like a two-dimensional map. So this is like the complex. You can think of this as a complex phase of the order parameter. So the amplitude of the order parameter is the radial coordinate, and the azimuthal coordinate is the phase of the order parameter. So then the initial state, as I said, is just a laser, so it has a well-defined phase. So that's before I do anything. This is just a spin polarized. They are pointing in the x direction. The other phase is the BC of the particles where I have selected a specific number of excitations. So, and you see that I have now restored, the phase symmetry. However, as you can see, the red is outside. What does it mean? It means that I have a large order parameter. So the amplitude of the order parameter is still large, and that's what makes the BC non-trivial. So the BC non-trivial means that you have a well-defined order parameter that has an unknown phase, so you just average over the order parameter, you get 0, and that's fine because the number equals conserved. But nevertheless, the amplitude of it, you can measure it, and here we can measure it, it's large. So the fact that if you just took, say, a thermal state, you would see a red inside. Okay, just the thermal state, the boring state is when the red is inside. So you don't have a lot of order parameters. You have a lot of order parameters, you just don't know where it's pointing. And so you can also do something fun, which is to measure the number of particles, but not post-select it. And now you get something that has both fluctuations, so you have increased the fluctuations of both. Okay, that's it. So we did some experiment. There was some agreement with the theory. I want to spend 2 minutes to say why I think it was interesting. First of all, because it's a method to try those quantum computers. I think this idea of using quantum circuits is a way to describe quantum mechanics in a useful way. As Jonathan taught us, you can really, do very nice fundamental quantum mechanics using circuit theory. So I think circuit theory was developed in the quantum computing community. Okay, that's okay. So. Conclusion, during the last couple of years, we've done several works using quantum computers to simulate interesting effects. I've discussed these first two. It was the Einstein topological phases, the non-local phase you've heard in the movie, long-range interactions, that was Moore's PhD project, quantum state encoding, that's something that Matan worked on. And also we did something about quantum error correction. This is with Sorin. So what is nice about all those papers is that, first of all, the last leading author is a really nice person, but also that in each of these events there was some simulation that came, some experiment that came out of the quantum computer, and it agreed or disagreed with the theory. So we really use the quantum computers for something. Where are we going? I'm trying to propose, and some of you may be in the committee in ISF soon, and don't forget this talk that was very nice. You should really continue funding it, about how to use the ideas to go. So we've used until now very small number of qubits. So what can we do? We have more qubits. We can try to use those ideas from mesoscopic physics to try to benchmark these quantum computers further. And so there is this on page 2 of the proposal, you will see that you rejected last year. Okay, I'm just mentioning that enhanced, but nevertheless, it's okay. I understand it. There were better proposals, but so this is a plot you will see on page 2. The idea is that we are here in the intermediate regime. Okay, that's the idea I want to see, is that we have quantum computers that on the one hand they are very large. We have, say, now we have quantum computers with hundreds of qubits, but the coherence is not as good. So you cannot just do any circuit you want. You don't. That's maybe many years from now you could do fault tolerant QPUs, but for the moment you can couple few qubits between them, but you cannot couple all the qubits together. You cannot have a global coherence of the whole QPU. So that's very much like mesoscopic physics, in which that in mesoscopic physics, the electrons, they have some local quantum effects. I mean, whether a material is an insulator or a metal, it depends on the quantumness of the problem. These are not just balls that move randomly diffusively. So it's a quantum problem, but nevertheless, there is not necessarily a whole quantum coherence on the whole device. So that's the regime that we are, and that's why I believe. We have some interesting projects. One of them is on the archive, and David and Shachar are also working on extend these ideas. about diffusion and thermalization, questions that are very common in the field of mesoscopic physics to benchmark those quantum computers, and I thank you for your attention.
In your abstract, you indicated that you mentioned how to program a quantum computer. I think, if my memory serves me correctly. So let's imagine I want to buy a quantum computer to solve a hard problem like combinatorial optimization.
Okay, so combinatorial optimization is really out of the scope of this presentation. It's a whole interesting field. Protected by IP, so I cannot tell you what we are doing.
But everybody else is doing.
No, but I think, I'll be glad to discuss it with you privately. Honestly, it's not clear whether this advantage of the quantum computer is significant for quantum optimization, for optimization of combinatorial problems. So you need to, there are many caveats in these questions. There are other applications like quantum simulation, also quantum chemistry so there is a beautiful presentation by Matthias Treuer, who is the head of the Microsoft quantum effort, and he starts with many applications, and then he says, okay, this is not relevant, this is not relevant, this is and the only one he's left over is quantum chemistry, which is some sort of quantum simulation, not a physics quantum simulation, but a chemistry quantum simulation. So I think that the real reason for building a quantum computer is this direction. And then there is the other direction, which is Shor factorization. The problem is that we have, anti-Semites that are building, post-quantum cryptography. I say, but guys, we didn't build the quantum. You are stealing the bread out of our mouth. Okay, the anti-Semitic was a joke, of course. So even that is not clear whether people do really need factorizing quantum problems. So, why people should invest in quantum computers is a question that, people need to seriously ask themselves. I think, in terms of basic physics, yeah.
So would it be fair to say that what you're actually using, the hardware you're using, is more of an analog computer than a digital computer?
No. Why?
I don't know, that's my question.
Okay, so there is a theorem that says that analog computers cannot work. In quantum information. No, I'm not an expert, but I know that people from information theory tell you this, because the reason is that you have errors that they propagate. So an analog computer, instead of having 0 and 1, you have a continuous of 0 and 1. And then you would say, for instance, think of pictures. Why do we store pictures in 0 and 1? After all, I don't really mind if that's exactly that color, right? I want some colors. It would be naively more natural to store an image with some analog bit, right, that goes between 0 and 1. The problem is that once you have an error, you don't want to know how to correct it. And so that's why quantum error correction is so fundamental to quantum computers, where there is a statement that if you are good enough, then you can correct those errors. Now, for classical computers, it's very easy to correct errors. And I give you an example, which I think for me it was, when I first heard it, it was very instructive, is the example of a switch of the light. Now, we all use it every day, but we don't really think about how precise it is, right? You turn off the light. How many times in your lifetime it happened that you turn on the light and randomly you say, oh, there is a 0, it could click off, right? But it never happens. The reason it never happens is that there is a lot of friction. And there is enough friction so that when you press it, you don't feel it, but it's enough friction so that there is, if there is a low alene, an explosion close to us, it will vibrate a little bit and then the click turns back to where it was. And that's because you are sort of measuring all the time. But in quantum physics, this is not allowed. You cannot use friction. So you cannot restore, your 0 and 1. And you need to be very, very smart. So you're right that in a sense, the quantum is analogous because you are in a superposition of 0 and 1. Yes.
There's a question in the chat from Hanan.
Yeah, Hanan asked how many qubits, what's the, how many,
So in the chat, okay, how many qubits are required so that you can't run the same simulation you showed on a classical computer? So that's a very good question. The answer is dependent on the application. So okay, and if you ask about an exact simulation, then you can have until maybe 20, maybe 30 qubits. Probably around 20 is the maximum, because 10 to the 20 is a million times a million is already something large, and that's it. 20, 25, I don't know. But there are better than that. I mean, classical simulations are not just wave vector simulation, and there are some models for which I've shown you one, all right? I've shown you a 50-qubit simulation because the model was very specific. Now, the debate I discussed about the IBM problem was that they solved the problem and said, this problem cannot be simulated by classical means, and they tried to do that, it did not succeed. And then other guys were better in classical simulation demonstrated this is possible. So the question of the limit it's related to the question of quantum advantages. And what is when does exactly quantum advantage comes is not known. It is nevertheless worth mentioning the quantum supremacy experiment by Google, which I believe was really a breakthrough, in which it exactly showed that. So they took a 50-qubit processor, and they demonstrated that they were able to do some calculation that for the quantum computer, for classical computer, would take much longer. Now, the only problem is that who cares about the calculation? But yeah, so the answer is, yeah, it depends on the circuit, it depends on the question you're asking.
You mentioned at the beginning these mid-circuit measurements, quantum computers. You didn't. The photon one.
It's recorded. I mean, it's not.
At the beginning, you said something.
Oh, measurement-based quantum computer.
Yeah, what does it mean? I mean, you mentioned dissipation now, but measurement is a type of dissipation.
Yeah. So measurement-based quantum computer, So it's a different idea. The idea is that you prepare a quantum state, okay, a very entangled quantum state, but always the same. It's a cluster state, same. And then you start applying unitaries and measurements, mostly measurements. Yes, you start measuring that state. And so it's, I mean, when I say dissipation, I mean something that is uncontrolled. So if you can, measuring precisely, know exactly what you are doing can help. I mean, you have, let's say, in fact, quantum error correction is based on mean-sequence measurements. So measuring in between is a tool that quantum information theory can use. What it cannot use is, the difference between dissipation and measurement is that in measurement, you are extracting that entropy to yourself. So you are learning something out of it. In the dissipation case is your enemy, which is the environment that is learning something about your system. And that's the difference. So if you can use, if you measure then use that information, that's useful. That's measurement with quantum error correction schemes. They are mostly based on this idea that you extract some information out of the system. That's fine. But if your enemy is if you're coupling to something that you then have control to, that doesn't work.
Yeah, but mid-circuit measurements exist already. Like quantum computers are there; they can do that.
Yeah, they exist. We are actually there is a paper, there is a work that is mentioned by Abbas about thermalization, and we are using those mid-circuit measurements. They are noisy. They are more noisy than usual measurements, and so he had to, even for a 4-qubit system, he had to work very hard to make that sigma.
Mitigate
smaller.
To mitigate.
Mitigation is that, mitigation didn't really happen as far as I remember. It was mostly choosing the right computer. There are different series of quantum computers, so there are those. Yeah.
So in what sense do you have? Can you say that the laser has less queries than Bose expansion? Message in
Yeah. So in a laser, I'll explain. It's a technical question. I'll explain to you. I'll explain to you. But let's. I think we'll keep the audience to much.
Again.
Okay.